Hello and welcome back. In the previous videos, we built a complete understanding of how signals behave in a high-speed SerDes system. We saw how signals propagate through the channel, how they are distorted by loss, reflections, crosstalk, and noise, and how equalization is used to compensate for those effects. But this leads to a critical question: how do we know if the system is actually working? How do we determine whether the signal quality is good enough for reliable communication? Even after equalization, these signals are still not ideal. So instead of asking whether the signal's perfect, we ask a more practical question. Is the signal good enough to reliably recover data? To answer that, we need quantitative ways to measure signal quality. In this video, we're going to answer that by introducing some of the most important metrics in qualifying SerDes links. They are eye diagrams, bit error rate, or BER, and signal-to-noise ratio, or SNR. Let's start with one of the most common metrics for evaluating signal quality, the eye diagram. An eye diagram is created by taking many bits of a signal and overlaying them on top of each other in time. This allows us to see how the signal behaves over many bits all at once. Instead of looking at a single waveform, we are observing the statistical behavior of the signal over many transitions. When plotted this way, the waveform forms a shape that looks like an eye. The eye diagram provides two key pieces of information: vertical opening, which represents voltage margin, and horizontal opening, which represents timing margin. As we've seen, the center of the eye is the best spot for the receiver to sample the signal. If the eye is wide open, it means the receiver has a large margin for sampling correctly. If the eye is mostly closed, it means the signal is difficult to interpret and errors are more likely. The shape of the eye diagram reflects all the impairments we discussed earlier. ISI closes the eye horizontally, noise reduces the vertical opening, and jitter shifts the signal in time and reduces timing margin. This means that the eye diagram is a single visualization that combines all signal integrity effects. Let's move on to the next important metric, bit error rate, or BER. BER measures how often errors occur in a communication system. It is defined as the probability that a received bit is incorrect. For example, a BER of 10 to the power of minus 12 means one error in every trillion bits. A BER of 10 to the power of minus 6 means one error in every million bits. In high-speed systems, extremely low BER values are required to ensure reliable operation. In high-speed communication systems, these signal quality metrics are often described as figures of merit, or FOMs. These are measurable quantities that help engineers evaluate how well a link is performing. Some of the most commonly used figures of merit include eye height, which represents voltage margin, and eye width, which represents timing margin. Both of these are used in eye diagrams. BER is itself a figure of merit. Another metric that is used is the signal-to-noise ratio, or SNR. Each of these metrics provides a different perspective on signal quality. Together, they give a complete picture of how reliably a system can transmit data. Let's take a look at the final channel metric we'll discuss, signal-to-noise ratio. SNR compares the strength of the desired signal to the level of noise present in the system. A higher SNR means the signal is much stronger than the noise, making it easier to distinguish between logical ones and zeros. A lower SNR means the noise is comparable to the signal, increasing the likelihood of incorrect decisions. As SNR decreases, it becomes more difficult for the receiver to distinguish between logical levels, which directly increases the bit error rate. In practice, SNR directly impacts the vertical opening of the eye diagram. If noise increases, the eye becomes more vertically closed, reducing voltage margin and increasing the probability of error. While S and R can be used to better understand voltage margin, there is another graphical way that helps us understand timing margin. That is the bathtub curve. The bathtub curve shows the probability of error as a function of sampling time. At the center of the eye, the probability of error is lowest. As the sampling point moves toward the edges, the probability of error increases. This creates a curve shaped like a bathtub. The width of the flat, low error region represents the available timing margin. Let's now connect everything from this course. The transmitter generates the signal, which also contains clocking information. The channel distorts it through loss, ISI, reflections, and noise, and equalization in the transmitter and receiver is used to compensate for these effects. What remains at the receiver is a real, imperfect signal. We then use metrics like eye width and eye height, signal-to-noise ratio, and bit error rate to evaluate how well the system is performing. Taken together, this gives us a complete picture of a high-speed link. The transmitter creates the signal, the channel distorts it, the receiver recovers it, and the system is evaluated based on how accurately the data is received. Ultimately, everything comes down to a simple question: can we reliably transmit data over this channel? And the answer to that question is reflected in the eye diagram, the signal-to-noise ratio, and the resulting bit error rate. This brings us to the end of the SerDes Basics class. I hope you all found the information in these videos useful and informative.